At this point, I'd like to introduce a kind of random process, kind of noise process, which is stationary, but it's not white noise. It is, however, rather common and important in time series. Rather than have no autocovariance and no autocorrelation at any lag other than 0, it has autocovariance and autocorrelation at every lag. It's the first example of a whole class of random processes, which we'll study in detail later. We're going to take a look at a first-order autoregressive process, also known as AR1 noise. To generate AR1 noise, take whatever the present value is and multiply it by some constant phi, which is the autoregression parameter. Then add a white noise value and you'll have the next AR1 noise value. Repeat this process ad infinitum and you'll have an AR1 time series. So AR1 noise is defined by this equation. The present value is autoregression parameter times the previous value plus white noise. Now the expected value of the white noise never changes. Different values of the white noise series are uncorrelated. That's the way white noise is. And we generally insist that the white noise process is a zero mean white noise process, so its expected value is 0. Now, we can apply this definition recursively. If this value is phi times the previous value plus white noise, that's phi times the previous value to that plus white noise, etc., 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 etc. And we can therefore say that it has this particular form, which is kind of interesting looking. We can even recurse the process infinitely backward in time to see this. And we can then use the fact that the expected value of the white noise process is 0 to compute the expected value of the AR1 process. And it turns out to be this infinite series of terms involving expected values of the white noise process, which are all 0. So it has an expected value of 0 itself. So an AR1 process is a zero mean noise process. We can also compute the variance, that is the variance of an individual value. Once again, we will use our recursive formula to compute the expected value of the AR1 value squared. We get this formula, we can expand it into the expected value of this product of terms, and we end up with this complicated formula with sum over two different variables that involves the expected value of products of the white noise values. Now the expected value of products of the white noise process is going to be 0 unless it's the same white noise value. Because zero mean white noise means the expected product is the variance of the white noise process, that's why I wrote a subscript W on the sigma squared, times the delta function of j minus k. So its expected value turns out to be exactly that. What we end up with is that the variance of our AR1 process is this sum of powers of our autoregression parameter times the variance of the white noise process times the Dirac delta function of the difference between the index values. And that means that most of the terms in the double sum end up being 0. The only ones that aren't are those for which the index values are the same. And that means we end up with this formula right here for the variance of the AR1 process. Now, if the parameter phi has an absolute value which is less than 1, and it's a pretty standard algebraic result to evaluate that series, and we get this quantity here. And then we'd have that the variance of the AR1 process is equal to the variance of the white noise process divided by this factor. However, if the autoregression parameter is greater than or equal to 1 in absolute value, then the sum does not converge. It diverges. The sum, as we go to infinity, goes to infinity. And in that case, the variance of our AR1 process ends up being infinite. Well, this is generally undesirable behavior. In fact, it's usually unphysical behavior. Such an AR1 process is called explosive. The covariance between different values of the same AR1 noise process, when the lag is not zero, would look like this. We can use the fact that it's zero mean and reduce it to that. Then we can use the recursive formula, the recursive form, to compute this just like we did for the variance, which is the same as the autocovariance at lag zero. Once again, we end up with a double sum that involves the expected value of products of white noise terms. Once again, those products of white noise terms will be non-zero only when their index values are identical. So we can again go through the algebraic manipulations and boil it down to this term right here, which is similar but not identical to what we had before. That means we've got a similar sum. We can apply the same algebraic relationship that we did before and end up with this. We have that the autocovariance of two different noise values from an AR1 process is equal to the same variance it had before times our autoregression parameter raised to the power of h, which is the lag between the two time index values. That's when the second one comes after the first one. Now, this does not depend on the particular index value, so it's time translation invariant. And since AR1 noise has a constant mean, which happens to be 0, and time translation invariant autocovariance, it is a stationary process. We can sum up. By its first two moments, the expected value is 0, and for any lag which is positive, negative, or 0, the autocovariance at that lag is the variance of the process itself times the autoregression parameter raised to the power of the absolute value of the lag. The autocorrelation function is therefore just this. It's the autocovariance at lag h divided by the autocovariance at lag 0, so it's equal to the autoregression parameter raised to the absolute value of the lag. We've now introduced an AR1 noise process, and this, as I say, is long before we consider the whole class of noise processes of which it's a member, just because I want to give you an example of a purely random process which shows autocorrelation. Also, it is a representative, a very common one, of a whole class of processes that we'll spend a good deal of time on later on. Here's an example of some random noise generated using an autoregression first-order model. This is AR1 noise. Of course, it's just one realization of AR1 noise. Now, it has a lot in common with white noise. It jiggles around randomly. But it also has a very different property from your typical random noise. Typically, your random noise, one value doesn't care about any other value. They're all independent, and they're all unrelated to each other. But for AR1 noise, different values are strongly related to each other, especially since I've chosen this to have an autoregression parameter of 0.95. That's very close to 1, which makes this a very strongly correlated autoregression first-order process. Notice that when the value gets up high, it tends to stay up high for a good long while. It takes a while for it to finally wiggle its way back around 0. That's because each value is 95% of the preceding value, plus some random white noise. When it gets down very low and negative, it tends to stay negative for a good long time. It takes a while for it to randomly wiggle itself back to 0. So it has a lot of persistence in it, but do be aware it doesn't have infinite persistence. Each value is only 95% of the previous value plus white noise, so it doesn't persist forever. It does have a tendency to work its way back to 0 over time. If we compute the sample autocorrelation function of this AR1 process, we get this. At least that's what the vertical bars represent. They represent the autocorrelation function value at various lags, and I've computed it for lags from 0 up to 100. The red line shows what we would get theoretically, and that's also what we would get if we had an infinite number of these AR1 noise values. So we can see that the observed autocorrelation function, the sample autocorrelation function for an observed AR1 noise process, it does follow the theoretical infinite size limit pretty closely, but not exactly, because let's face it, it was random. And as long as we have a particular realization that doesn't last forever, it's going to include randomness in everything about it, including its autocorrelation function when estimated from observed data.